Welcome to The Explainer. Today we are rewinding the clock all the way back to the beginning. No, not just the beginning of time. We're talking about the moment before time even existed. We're going to explore how, in the first 10 nanoseconds, the fundamental rules of our universe got written in a flash of cosmic fire. All right, so here's our roadmap. We're going to start from this single point of pure potential. From there, we'll watch a primordial firestorm. See a time when the fundamental forces of nature were actually one and the same. And then get to the crucial moment, mass itself was born. And finally, we'll witness a great annihilation that set the stage for, well, everything we see today.
So to really understand where we're headed, we have to start at the very beginning. And I mean the beginning before the beginning, when there was nothing. Okay, that's a pretty mind-bending idea, right? It's tough to really wrap your head around, but it is the starting point for our entire reality. Just try to imagine it, our whole universe, just erupting from a state of absolute non-existence.
So picture this, a single, mysterious point. And inside that point is all the potential for every star, every planet, every single one of us. It was all governed by a set of rules we now call the laws of physics, and they were about to unfold in the most dramatic way you can possibly imagine.
So from that single point, everything changed in an instant. This was the primordial firestorm, an explosion on a scale and intensity that is just, truly unimaginable.
I mean, what an image, right? The universe kicked off as this unbelievably hot and dense firestorm. But here's the key thing. It wasn't an explosion in space. It was the expansion of space itself, happening uniformly and infinitely in every direction at once.
To really get a feel for the cooling we're about to talk about, you've got to start with the heat. We're talking temperatures of 10 quadrillion times 10 quadrillion degrees. It's a number so big it almost loses all meaning, but it gives you a sense of the extreme conditions of these very first moments.
And this right here becomes the main theme of our story, the engine of all change. Every major event that happens in these first nanoseconds happens for one reason. The universe is relentlessly expanding, and because of that, it's cooling down.
And that cooling happened fast. In just a tiny fraction of an instant, the temperature plummeted. Now, of course, plummeted is a bit of a relative term here. It dropped to 10 quadrillion degrees, which is still so ridiculously hot it makes the core of our sun feel like an ice cube.
So what this means is that this early cosmic soup was just pure chaos, but it was a perfectly mixed chaos. Everything was smashing into everything else so often that all the energy was distributed perfectly evenly. You can think of it like a perfectly blended, super high-energy particle smoothie.
Now, to really speak the language of the early universe, we kind of have to learn the local currency. And back then, that currency was the electron volt, or EV. In quantum field theory, pretty much everything, a particle's mass, its energy, it's all measured in EV. It's the key that's going to unlock all the numbers we're about to see.
Okay, let's jump into a time when the universe was, believe it or not, a lot simpler. It was an era of perfect symmetry, where forces were unified and particles had no mass.
This timeline is just wild. It shows you how unbelievably fast everything changed. We're talking about picoseconds. That's trillions of a second. In that time, we go from a totally symmetric, massless state to the Higgs field kicking on, and then, almost instantly, the heaviest particles start vanishing. The pace of change was just breathtaking.
I mean, this is a reality that is just completely alien to us. Can you imagine a universe where two of our fundamental forces are merged into this single electroweak force, where every single particle has zero mass, so everything is just zipping around at the speed of light? This state of perfect symmetry, though, it was about to break.
And this brings us to what is maybe the single most important event in this entire story, the moment particles actually got their mass. This is where the universe as we know it really starts to take shape.
Just look at this shift. The universe expands, it cools past this one critical temperature, 246 giga-electron volts, and boom, the Higgs field suddenly activates. It's like a switch was flipped across the entire cosmos. That unified electroweak force splits into the separate electromagnetic and weak forces we know today, and a whole bunch of particles suddenly get heavy. The symmetry was broken, and it was broken for good.
And just like that, particles that were once totally massless become these cosmic heavyweights. The W and Z bosons, they get massive. The Higgs boson itself gets mass. But here's the really weird part. Look at the top quark. At 173 GeV,
It becomes the heaviest elementary particle we know of. In a really strange twist, it's actually heavier than the Higgs boson that gives it its mass in the first place.
But here's the thing. As soon as these heavy particles got their mass, the clock started ticking. The universe was still cooling, and it just wasn't energetic enough to create them anymore. Their time was already running out.
It happened in stages, heaviest first. The top quarks, being the most massive, gone, first to disappear. Then came the Higgs, W, and Z bosons. Then, the next tier of quarks and leptons followed. And as each type of particle and its antiparticle annihilated each other, they dumped all their energy back into the lighter particles that were still around. It was a cascade of disappearance.
And while all this is happening, as space gets a little less crowded, another one of the fundamental forces starts to, well, flex its muscles. The strong nuclear force, which is carried by gluons, begins to bind quarks together. This is the force that will eventually hold our protons and neutrons together. And its incredible strength, we're talking literally metric tons of it, was starting to make itself known.
So after this cosmic gauntlet, after this great filtering process, who's left standing? This is our crew. After just 10 nanoseconds, these are the massive particles left to build the next stage of the universe. You've got the familiar up and down quarks, the electron, and a few of their slightly heavier cousins, whose own time, by the way, is also numbered.
And this leaves us with the final and most profound takeaway from these first 10 nanoseconds. In all of this creation and annihilation, there should have been a perfect one-to-one balance between matter and its opposite, antimatter. They should have completely wiped each other out, leaving behind a universe with nothing but light. The fact that you and I are here to even think about this question means that for some reason we still don't fully understand, a tiny, tiny fraction of matter survived. Our very existence is the result of a flaw, an imbalance in that perfect initial symmetry, and that might just be the most important rule the universe ever wrote.